Now we're going to start looking more in depth into specific types of functions, starting with linear functions. I assume that you guys have some foundational understanding of this list of concepts that deal with linear functions. The slope formula, where you take the rise over the run, the rise being the difference in y values between 2 points, the run being the difference in x values for the same 2 points, and then dividing them. The slope-intercept formula, y equals mx plus b, where if you solve for y in a linear equation, the slope will always be the coefficient of x, the y-intercept will always be the constant. There are some reasons why that occurs. You can actually use the slope formula with the y-intercept and a variable point plugged in and derive this formula from that. The standard formula, which is where you basically get your x and y's on the same side of the equation. A, b, and c are all just constants. The point slope formula, which is again derived from the slope formula by essentially multiplying both sides by the denominator and replacing the point x2, y2 with a variable point. You can get this formula. It's very useful if you're given a point and a slope. You can use them, plug them in for m and the x1, y1, and that allows you to then solve, find the equation of the line. You could even put it in slope-intercept form once you solve for y. Then we have horizontal and vertical lines. Horizontal lines are y equals a constant. We call that b usually, but that's only because horizontal lines have a slope of 0, and when you plug a 0 in for your m up here, all you're left with is b. And then the vertical line is x equals a number. That's your a value, x equals a being the x-intercept, in a similar way that b is the y-intercept. Okay, we just use alphabetical order there, right? X comes before y and a comes before b. And so these are sort of some general formulas that you get when you look at lines. But really, the slope-intercept formula is the function notation, right? You can put that in function notation, and that's really the more useful one, the one that you see most common. It's also unique for every line, okay? Whereas the point slope formula is not unique for every line. It's different for every point that you choose on the line to plug in. But when you simplify it and put it in slope-intercept form, you'll always get a unique linear equation for each line, okay? All right, and so there are some very important features of lines. If you were to have a set of data or a table that gives you inputs and outputs for a line, there are some characteristics that you'll find. Because the slope is consistent, that is that for a consistent horizontal change or change in the x values, you'll have the exact same change in the y values for a line, okay? And so as a result of that, if you were to have some values, let's say we wanted to just start plugging in, increase by 1, just because it's easy to calculate, 0 to 5, then the y values, in order to be a line, the y values would have to increase at a constant rate. So if we were to start at, say, 10 and increase by 3, that would be an example of a linear function. No matter where you start, as long as the increase is consistent, always the same for a consistent increase in x, then you have a linear function. Okay, so as long as we have the same increase here, add 1, add 1, add 1, and over here you're adding 3, adding 3, adding 3, and so on. As long as those two numbers are the same all the way down, you have a linear function. Now, if you had a consistent increase on the left, but not a consistent increase on the right, then you would have something that's not a function, not a linear function. Okay, you'd have some other type of function potentially, but not linear. Okay, and it could be a decrease. It doesn't have to be an increase. A decrease would then be a decreasing function, whereas the increase would be an increasing function. Okay, so that's going to be very important to be able to find that difference between each pair of points and make sure that it's consistent. Now, the slope of the line, the slope, ends up being the ratio of these two differences. So here, the ratio of the difference on the right to the difference on the left, 3 to 1, right? 3 to 1 is going to be the slope. Okay. Now, if you had a gap of 2 on the left, so if you went from 3 to 5, right, that's an increase of 2. Well, correspondingly, from 19 to 25, you actually have an increase of 6. And so when you divide them out, 6 to 2, you still get that same slope of 3, right? The same ratio. So the simplified form will be the same. Okay, so that works for lines. Let's see. Now, we call this, another name for it is the average rate of change. We've seen some things like the average rate of change before. The average rate of change, if I were to take any general function, the rate of change at any point is different than at any other point, right? So, for instance, here, the rate of change is increasing very rapidly. It's spiking up very quickly. Whereas over here, it's actually decreasing more gradually. And so the rate of change changes throughout a function, generally speaking. But the average rate of change is essentially the slope of a line that connects the 2 points. Okay, so the average rate of change averages those out, or I don't know, tries to account for all of the points in there, the rate of change at all the points. And so to find an average rate of change, you're looking really for the slope of the line, right? So if this was a function, we'll call it g of x, or I'll call it f of x. But it's not going to be linear, so I don't want to confuse you with the other f of x. So if this is f of x now, and I have 2 inputs, we'll call them a and b, then the corresponding outputs are f of a and f of b. And so the average rate of change or what I'm going to call the ARC, I'll sometimes abbreviate that as ARC. The average rate of change is simply going to be the difference in the y values. It's basically a slope, right? So it's the difference in the y values. It'd be f of b minus f of a over the difference in the x values, b minus a. All right? So this is your average rate of change for a general function. What's interesting is if the function is a line itself, then the average rate of change reduces to the slope of that line. Okay? Let me give you a couple examples. Let's take a nonlinear function first, and then we'll do an example with a linear function. So let's say you have a nonlinear function, something like, I don't know, x squared plus 3. That's a nonlinear function. And let's say we wanted to find the average rate of change from x equals 1 to 3. Okay? The average rate of change from 1 to 3. Then what we do is we use this formula. 1 and 3 are the a and b values respectively, right? So we need to find the function values. F of 1 is, well, 1 squared plus 3 is 4, right? 1 plus 3. And f of 3 is 3 squared plus 3. 9 plus 3 is 12. And so the average rate of change is going to be f of b or f of 3, I should say, minus f of a, which is 1, all over b minus a, right? F of b, f of a, then b and a. And so when I plug those in, f of 3 was 12, so that gives me 12 minus f of 1, which is 4. 3 minus 1 is 2. 12 minus 4 is 8. 8 over 2 is 4. So the average rate of change is 4, right? It's a rise of 4 to a run of 1. Okay. Now this is not a linear function, right? It's a parabolic function. Yeah, parabola. Shifted up 3 units. But the average rate of change is linear. It's a slope from one point to the next. If you can imagine this graph being shifted up 3 units, then from x value of 1 to 3, the slope of the line connecting those 2 points would then be 4. Okay, that's what we're looking for. But again, if this original function were linear, then the average rate of change and the slope are the same. Give you a quick example of how that would work out. Let's take a function to be linear. Let's go with, let's say 5x minus 9. That's a linear function. It's in slope-intercept form. Well, the average rate of change then, and let's go from, so find average rate of change from x equals 2 to 7. We'll just throw a couple numbers in there, right? Well then, what we're going to need is f of 2 and f of 7. When I plug them in, I get 5 times 2 minus 9. That's 10 minus 9 is 1. And 5 times 7 minus 9 is, what's that, 35? 35 minus 9 is 26. And then the average rate of change is going to be the change in the outputs, 26 minus 1, over the change in the inputs, 7 to 2. Okay? Using the second one first and the first one second, so final minus initial. And what you'll end up with is 25 over 5, which reduces to 5. Average rate of change is 5. Should match up with the original slope in the original function. Okay? So there's your average rate of change. Okay, now, some other interesting features, or other things that we can do, I should say, with linear functions, is we can combine them. You can have multiple linear functions. You could have, let's say, f of x equals 2x plus 4 and g of x equals x minus 8, and I can combine them. We could actually find x values that make maybe f of x equal to 0, right? Solve f of x equals 0. So all you do is you replace the f of x with 2x plus 4, set that equal to 0, because f of x is equal to 2x plus 4, you can replace those, and then obviously solve for your x. And I'll do that quickly, and you get an x value of -2. Okay? So you're solving an equation. Now, of course, this would be a solution set, because you're solving an equation, so your solution set would be the set containing -2. Okay? You can also solve other things. You could solve inequalities, right? You could solve, let's look at, solve g of x less than or equal to 0. Okay, so g of x less than or equal to 0 is just taking the x minus 8 less than or equal to 0, add the 8 to both sides, you get x less than or equal to 8. This is our interval, and this is our solution to that inequality. And so I would just say, let's see, x less than or equal to 8 is negative infinity up to 8, including the 8. So this interval solves the original inequality. We can even combine the two functions together and solve either equations. You could set them equal to each other. We could do inequalities, something like f of x greater than g of x. Right? I could set them equal, I could make an inequality out of them either way, in which case I'm taking, replacing each function with its equivalent expression. Like 2x plus 4 is greater than x minus 8, and then I just solve using my inequality properties. I subtract off the 4 here, I get 2x is greater than x minus 12. I subtract off the x, and I get x is greater than negative 12. This interval, the corresponding interval I should say, from negative 12 to infinity, would then solve the corresponding inequality. Okay? Alright, so that's an example of some other things you can do. Now you could even do this graphically. Right? So if I didn't actually know the equations for the function, I could look at the graphs and still solve equations and inequalities. Let's see, let's do a different color. Let's make the graph, put the axes. Blue is going to be too close. No, let's do this. Let's do, debating on the color here. Let's go with black axes. And let's make a red f of x. And let's make a green g of x. Oops. And let's get the intersection point. Let's put that point of intersection at, I don't know, 2, 1. All right, there's my intersection point at 2, 1. So there's a graph. There's two functions intersecting. They're both linear functions. I can solve lots of different equations and inequalities here. I could find, I could solve f of x equals g of x. Well, that's just where the two functions are equal. Where are they equal? Where they share the same point. Okay, where the same point solves both functions. That would be at the point 2, 1. Now, if you're solving this equation, you're looking for x values, right? We would be looking for the value of x if I plugged in the functions. If I knew the functions, I don't know the actual equations there. But if I did, I'd plug them in, I'd solve for x. So we're looking for just the x value of 2. Okay, and so again here, our solution set, because it's an equation, would be the set containing 2. That's your x value. Okay. Now when you check that, if you were doing this with the equations, if you check that 2, it would make both sides equal to 1. That's what the 1 would represent, the output from each function. Okay. You could also solve inequalities. Or my eraser's leaving behind some markings here. Okay, I could also solve things like, I don't know, g of x is greater than or equal to f of x. Okay? Well, in this one, I'm looking for all x values, right? You're always looking for x values on these. Looking for all x values that make the g of x function higher, greater, than the f of x function, which occurs on the left here. Okay? In fact, if you started at 2, it'd be everything to the left of 2. That would make the g function higher than the f function. So we'd be looking at all x values that are less than or equal to 2. And I include the equal because at 2, the two functions are equal to each other. Okay? And so I don't have to actually solve. I'm not like trying to do any arithmetic or any algebraic properties here because I don't know what f and g are. I don't know the equations to these two graphs. But based upon the graph, I can find the relationship. I can find the values of x where the relationship g greater than or equal to f is true, wherever g is above the f function. Remember, these are the outputs. So you want the outputs of g to be greater than or equal to the outputs of f. That means the y values are higher in g than in f. Okay. Okay. Now, there are a couple other topics in that deal with linear equations that I'm going to refer to a couple other videos using your graphing calculator. There's a couple videos, one I believe called Calculator Basics and one called Linear Regression. They're important topics that I'm going to refer to those videos to finish this off.